Today we are going to be looking at LT2. I can verify similarity through a sequence of transformations, including dilations. However, we're going to be focusing on the verifying similarity portion of that target. So verifying similarity, we can verify that two polygons or two figures are similar if it meets two criteria. The first one is that their corresponding angles are congruent and the measures of their corresponding sides are proportional. So when we're saying corresponding angles mean if we are looking at triangle ABC, so triangle ABC, and we are going to be verifying if it is similar to triangle XYZ. That means that angle A has to be congruent to angle X, angle B has to be congruent to angle Y, and angle C has to be congruent to angle Z. So if we look at our figures, you should notice that the angles are labeled with these arcs. And if the arcs are the exact same in two different figures, that means that those angles are congruent. So looking at this, we can see that angle A is congruent to angle X, angle B is congruent to angle Y, and angle C is congruent to angle Z, because each of those angles have their own individual arc marking. It's either one arc, two arcs, or three arcs, and it matches with an angle in the second figure. So that would satisfy that the corresponding angles are congruent. The second criteria that must be met is the measures of their corresponding sides are proportional. So to find out if they are proportional, we're going to be using our scale factor ratio of dilated over original. So if I am looking here, that means that side AB right here, I take that back, XY, since we're starting with our dilated, XY needs to be proportional to AB. And whatever that ratio is, needs to be equal to the ratio of YZ over BC, and also needs to be the same ratio as either ZX or XZ, however you want to say it, over AC. So if all of this is true, if it's all true, then we can say that triangle ABC is similar to triangle XYZ, and that's what that symbol means. It's not equal, but it's similar. Okay, so let's continue our lesson. We are going to work on example 1. So example 1 says graph the original figure and its dilated image, then verify that the dilation is a similarity transformation. So let's first graph our pre-image. You can go ahead and pause your video. At this time I'm going to add that on and draw your pre-image. Okay, So your figures that you drew should look like this. Our pre-image A, B, C, and then our image D, E, F. And so we need to verify that this is a dilation. Looking at it, I can see going from ABC to DEF, this is going to be a reduction in size if, in fact, they are similar to each other. So the first thing that I want to look at is, are the corresponding angles congruent? Well, I can see that angle A and angle D are both right angles, and we know all right angles are congruent. And if we were to take a protractor out, which we don't currently have, but if we were, we would get that angle B is congruent to angle E, and angle C is congruent to angle F. So that meets one criteria. Our next criteria that we have to look for, remember, is that the measures of their corresponding sides are proportional. Okay, so AB corresponds to side DE. And remember, when we set up our scale factor ratio, it's dilated image over original image. So the length of DE is equal to 2.5, and I'm going to write that over my length of AB, which is 5. And if I were to reduce that, 2.5 over 5 is equal to 1/2. Now, since we don't know if these are similar, we have to check the other sides to see if they also share this same scale factor, this same ratio. So next I'm going to look at AC and DF. So again, my dilated image side is DF, and I would put that over my original, which is AC. And DF is 4 units. AC is 8 units. And 4 divided by 8 is also equal to 1/2. Our last side, we see that it's a diagonal length, so we will have to use our Pythagorean theorem to find the distance. So we are going to take for triangle DEF, my side lengths, I have 2.5, I'll square that, plus 4 squared, and 2.5 squared plus 4 squared is equal to 22.25. And if I take the square root of that, I get quite a long decimal, so we'll just round it to approximately 4.72. So my length of EF is going to be approximately 4.72. And then if I look at my side length BC, I'm going to take AB squared plus AC, so 5 squared plus 8 squared equals C squared, so 25 plus 64 equals 89 equals C squared, and the square root of 89 is equal to approximately 9.43. So BC is approximately 9.43. And if I divide those, remembering that we did round them, so 4.72 divided by 9.43, that gets us just about 1/2. So we would see that pattern. All sides have the same ratio when we are comparing them, which means that the sides are proportional. So our conclusion that we can draw from that is triangle A, B, C is similar to triangle D, E, F by a dilation of 1/2. Okay, looking at example 2, it says determine if two figures are similar by using transformations. Explain your reasoning. So with this problem, let's just say that our figures, our pre-image is A. So we would be dilating from A to B. Now if that was the case, this is going to be a reduction. Maybe. If they're not similar, meaning if the angles are not congruent and the side lengths are not proportional, then there isn't really even a reduction because it's not the same shape. There wasn't a dilation that occurred to get A to B. So looking at my parallelogram here, I can see, and we can even use patty paper to trace our angles, and we can see that angle, or all angles are congruent. I guess we don't have separate names for them. So all the angles are congruent, which is the first criteria moving towards seeing if these figures are similar. The next criteria, again, is seeing if the sides are proportional. So I'm going to look at first the top portion of both figures. So if I'm going from A to B, my dilated image would be the B, which that side length is 3. So that would be 3 over 6, which reduces to 1/2. And since it's a parallelogram, we know that the top line in both of those figures is going to be equivalent to the bottom side in both of those figures. So we don't really have to write that twice. We just know right away that those are going to be congruent and the same depending on the shape that they're in. So then if we look at our diagonal lengths, again using our Pythagorean theorem, so if I take the diagonal of the dilated figure, so that would be 1, 2, 3, 4, 4 squared plus 1 squared, so 16 plus 1, 17 equals c squared, so the square root of 17 equals c, and we are going to be relating that to the length in the pre-image, 1, 2, 3, 4, 5, 6, 7, 8, so 8 squared plus 2 squared, 64 plus 4, 68 equals c squared, so the square root of 68. So if I plug that into my calculator, the square root of 17 divided by the square root of 68, we get 0.5, which we know is equivalent to 1/2. So since the sides are proportional, you can see that the sides are proportional because, again, opposite sides in a parallelogram are congruent. We can say that these figures are similar by a dilation of 1/2. Now, if we had started this problem and I had said that the pre-image was B, our ratios would be opposite, and so you would say those figures would be dilated by a scale figure of 2. You would just reverse the order of your ratio. All right, so looking at example 3, determine whether each pair of polygons is similar, then verify that the dilation is a similarity transformation. Okay, so we can see we have 2 right triangles. Now the key here is, even though they have different orientations, one is turned around, we need to make sure that we are relating similar sides or corresponding sides. So the 5 is going to be that bottom leg of the right triangle, which is going to correspond to 8. So we can do 8/5 or 5/8 for the purpose of identifying similarity. It does not matter which order you put them in. So we have 8/5, and we are questioning, is that the same as the ratio of our second leg, which is 12 and 15? And since I put 8 in the numerator, I have to put 15 in the numerator. You have to stay consistent. And then, is that the same as comparing our hypotenuse, which would be 17/13? So if we divide 8 divided by 5, we get about 1.6. And then if we take 15 divided by 12, we would say that is about 1.25. And then 17 divided by 13, you get 1.307, and it goes on. So looking at that, are those the same value? They definitely are not. So we would say that these triangles are not similar. Because the corresponding sides are not proportional. Okay, so go ahead and work on the practice. Connected, each practice example should match very similarly to one of the examples, and we'll go over it in class. Thank you.